Cambridge Lower Secondary Science Learners Book 7, Chapters 5, 6, 7, and 9.
And welcome to The Explainer. Today, we're embarking on a massive rapid-fire science crash course. We are taking a full macro to micro journey through the hidden rules that dictate, well, absolutely everything around us. From the massive geological forces shaping our planet right down to the microscopic, invisible particles powering the device you're using right now. Okay, let's dive right into this.
I want you to kick things off by picturing three completely different things for me. First, a violently erupting volcano spewing molten rock. Second, an old apple sitting on your kitchen counter, slowly turning brown and getting kind of moldy. And third, the electric battery sitting inside your car right now. So what do these three completely disparate things actually have in common?
I know, it sounds like a total trick question, but the answer is that they are all driven by the exact same fundamental hidden rules of science. Whether we're talking about geology, biology, chemistry, or physics, there is this incredible invisible logic connecting the abstract concepts we learn in school to the everyday mysteries we see all around us.
To help us make sense of it all, here's our roadmap for this explainer. We'll be looking at our restless planet, the web of life, mastering the material world, chemistry hacks and hazards, the science of sound, and finally, controlling electrical currents.
All right, let's kick things off at the absolute macro level with Section 1, our restless planet, uncovering the geological forces right beneath our feet.
Just try to wrap your head around the sheer scale of geological time. Scientists have worked out that the Earth formed roughly 4,500 million years ago. It's almost unimaginable, right? Over this massive timeline, giant landmasses have drifted apart and violently collided. Look at the Urals in Russia, for example. Those are some of our oldest fold mountains, forming over 200 million years ago. But then compare that to the Himalayas. Those are the absolute newest fold mountains, formed a mere 10 to 25 million years ago. Honestly, geologically speaking, that is practically yesterday.
So you might be wondering, how do these massive mountains actually form? Well, it's all about tectonic plates. These huge continental plates are basically floating on liquid rock called magma. And get this, they move at roughly 4 centimeters per year. That's literally the exact same speed your fingernails grow. When one plate slides under another, we get what's called subduction. If they drift apart, magma erupts right through the cracks, becoming lava. And when they violently smash together, we get massive earthquakes and volcanoes, like the ones you see all along the volatile Pacific Ring of Fire.
Now let's zoom in a bit from those giant mountain ranges for Section 2, the web of life, how energy connects all living things.
Think of this as nature's ultimate biological energy highway. Fun fact, every single bite of food you take is basically just sunlight in disguise. It all starts with the sun. Producers, like plants, use that brilliant sunlight to make food. Then consumers, like herbivores and carnivores, come along and eat those plants, or they eat other animals. But the cycle doesn't just stop when a consumer dies. That's where step 4 steps in, the decomposers. Without them, our planet would literally just be covered in endless heaps of dead plants and animal waste.
And who exactly are these vital decomposers? Microorganisms. We're talking single-celled wonders here, like bacteria and microscopic fungi. They are nature's ultimate maintenance crew. You see, when they break down that moldy apple we talked about earlier, or a fallen leaf, they aren't just destroying it. They're actually recycling the organic matter, pumping those essential nutrients right back into the soil so the producers can start the whole magical cycle over again. They literally hit the reset button on the entire system.
Okay, let's drill down even further now. Section 3, Mastering the Material World, the elements and compounds that build our reality. Let's do a quick-fire comparison of our two major material players. On one side, we've got metals. These are your heavy-duty team players. They're solid at room temperature, shiny, malleable, meaning you can hammer them into sheets, ductile, so you can pull them into wires, and they are excellent conductors of heat and electricity. Now, on the exact opposite side, we have nonmetals. If they happen to be solid, they're dull and brittle. They'll just shatter instead of bending. They're terrible conductors, which, funny enough, makes them absolutely fantastic insulators. But wait, don't forget, nonmetals aren't just solid insulators like the plastic wrapped around your phone charger. The invisible air keeping us alive right this very second, that is a nonmetal mix. It's composed of 78% nitrogen and 21% oxygen. These nonmetals are gases at room temperature, which just goes to show that these fundamental elements are quite literally everywhere, quietly making our world work behind the scenes.
Now, what happens if you need a metal that's way stronger than what nature provided? Simple. You make an alloy. Think of making an alloy kind of like remixing a song. You take the same bass tracks but give them new beats to make something better.
Pure 24-karat gold is beautiful, but it's way too soft for a wedding ring, so we mix it with copper or silver to make a tough 18-karat alloy. Pure aluminum is super light but weak, so we mix it with magnesium and copper to create duralumin. That stuff is 5 times stronger and absolutely perfect for building airplane wings.
Moving right along into the laboratory for Section 4, Chemistry Hacks and Hazards. Safely testing and separating matter.
If you've got a mixture, which is where substances hang out together but aren't actually chemically bonded, you can use some real pro moves to separate them by exploiting their physical differences. Got iron filings mixed with sulfur? Just wave a magnet over it. The iron snaps right to it. Have copper sulfate dissolved in water? Use evaporation. The water turns to vapor, leaving these gorgeous blue crystals behind. And what about food dye mixed into water? You'd use simple distillation. The water boils into steam and then condenses right back into a pure liquid, leaving the dye completely behind. It's brilliant.
Okay, so what about testing those chemicals? For that, we use chemical indicators. I personally love to call these things mood rings for molecules. Imagine you have 3 clear liquids in front of you, and absolutely no idea if they're acidic, neutral, or alkaline. You just drop in an indicator. Something like red cabbage juice will instantly turn a bright, vivid red in an acid, blue in neutral water, and yellow in an alkali. Litmus dye does the exact same trick, turning red for acid and blue for alkali. It is basically a real-life, color-changing cheat code.
Of course, working with harsh acids and corrosive alkalis means you need strict discipline. Here are your absolute non-negotiable lab safety hacks. Number 1, always stand up while you work so you can step back fast if a spill happens. Number 2, safety glasses are a must. No exceptions. 3, park those bottle caps upside down on the bench to stop contamination. 4, cap your bottles immediately after you use them. And 5, always pour with the label facing up. That way, if a stray drip happens, it doesn't smear the vital hazard warnings printed on the bottle.
Let's shift gears entirely now for Section 5, the science of sound. We are riding the invisible waves of vibration.
At its core, sound is fundamentally made up of vibrations. And just like a bouncy ball, these sound waves can reflect off surfaces. The reflection of a sound wave is what we call an echo. And this works best on really large, smooth, flat surfaces, like a massive concrete wall. But echoes aren't just for yelling into canyons for fun. Bats use echoes to pinpoint tiny insects in the pitch dark, and boats send sound straight down to the ocean floor to measure the water's depth, just by timing how long the echo takes to bounce back.
But here is the absolute most crucial point to remember about sound. The waves absolutely require a medium to travel. They need a solid, a liquid, or a gas. Sound travels by physically making particles vibrate against each other. Therefore, in a vacuum where there are no particles at all, there is zero sound. Space is a vacuum. Which means, if space weren't a vacuum, we would actually hear the violent, massive, continuous explosions of our sun. But because of the rules of physics, the sun burns in complete and total silence. How wild is that?
Finally, let's zoom all the way down to the microscopic level for Section 6, controlling electrical currents, directing the flow of electrons.
If you want to understand how a circuit works, you first have to understand voltage. Voltage is essentially the electrical push. It is the energy per unit charge, usually provided by a cell or a battery, that literally drives the electrons through the wires. Without that vital push, your doorbell isn't going to ring, the light bulb in your refrigerator won't turn on, and your phone definitely isn't going to charge.
And why does that push actually work? Well, it all comes down to the fundamental law of attraction. Deep inside those wires are incredibly tiny particles called electrons, and they carry a negative charge. The golden rule here is simple. Opposite charges attract, and like charges repel. So inside a battery, the negatively charged electrons are aggressively repelled away from the negative terminal and heavily attracted straight toward the positive terminal. That continuous flow, that mad rush of electrons trying to get to the positive side, that is exactly what we call an electrical current.
Wow, we have covered an immense amount of ground in this explainer today. We've gone from 4.5 billion-year-old tectonic plates down to microscopic bacteria, from chemical alloys to the silent vacuum of deep space, right down to the tiny electrons zipping through your chargers. So I want to leave you with this provocative thought. Take a moment right now and just look around the room you're sitting in. Are you seeing the plastic, non-metal insulators keeping you safe from the electrical current humming inside your walls? Can you spot the alloys making up your door handles? Honestly, what invisible science is happening in your room right this very second? Keep questioning, keep observing, and I'll catch you in the next explainer.
Mind mapping of Chapter 5, 6, 7, and 9.